Hello and welcome back to Calculus 3, section 14.1 on vector fields. So we are starting our vector calculus chapter. This is the end of Calculus 3. We have to push through at least half of this thing as the semester is winding down, so pay attention. We are going to define the vector field. Again, guys, this is a mathematical construct, just like a vector is mathematical construct. Vector does not exist. We use it as a mathematical construct to portray certain things. For instance, a force or a human standing upright, right? That vector would be, I don't know, magnitude 6 at angle 90. So now, when you have a whole bunch of those vectors, infinitely many, you are going to assign to each point in a 3D space or 2D space a vector that is pointing in whatever direction it's pointing according to a formula. You are going to call that a vector space. The way to understand the vector space would be just simply turn the fan on, right? And you feel the force of the wind, right, hitting you. That means that each particle in that space is being pushed, right? And the direction of the motion of that particle, which eventually hits you, is going to be the, you think of it as a vector. So vector space is going to be electric field and magnetic field and gravitational field, but it's also, you can understand it as the currents moving in the sea, right, or the waves, or the wind, or with the wind you can talk about the tornado, hurricane, and all of these kind of things, right? So the field, whether it's two-dimensional, three-dimensional, is simply the entire space is filled with points, and to each point, each location in that space, there is a vector associated to that particular point. So let's write down the vector field dimension, two-dimensional version of the vector field, like definition, and then work on some examples. So, definition of the vector space. This is a 2D version. So let f and g be defined on region R of R2, a vector field. This is what we are focusing on. A vector field in R2 is a function f. Now, when you write this f, you have to put the arrow above because it's a vector function. So it's a function f that assigns to each point in a domain a point in y, right? A vector in y. So to each point of R, a vector f of xy, g of xy, notation, vector f with the arrow on top. Now in the textbook, obviously they are going to use bold, right, because they have put all of the vectors bold. Now your vectors from previous chapters were all lowercase and bold. Vector field is going to be uppercase and bold. In your notes, on your exam, and everything else, the homework, you will use capital F with the arrow above, so you don't have to go and make it bold and all of that kind of stuff. So the notation is very simple. We have vector field. Since it's a vector, we use the spiky brackets. It's a vector, so we use the arrow above, and that's that. We can also use the ij notation, right? So we can say it's just f of x, y, I with the hat plus g, x, y, j with the hat. So whatever notation you want. So this is definition. It's simply the vector space, I mean the vector field is the function which assigns to each point in the region a vector. So now to understand this, if I come up with any kind of vector field, say I have 2x and then I have 3x minus y, let's say this is the vector field. Don't let this x and y confuse you that your first location in here is the function f and your second location is function g. So this is not a point x comma y where the first one is dependent on x and the second one is dependent on y. No, they are both dependent on both x and y. These are locations for functions. So I have that the f function is 2x, only dependent on x in this case. The second one is dependent on both x and y. And we'll see, you know, some of the vector fields where y is in the first spot and x is in the second and so on. Now, what does this mean? Well, this means that at the point, say 5, negative 2, we have a vector, and now you compute. The vector will be 2 times 5, comma, 3 times 5, minus negative 2. So the vector is 10, comma, 12. No, 17. 10, 17. So that's the vector. You will go to a coordinate system. You will locate where 5, negative 2 is, and you will draw 10, 17 vector from it. So that would be this vector u. So it's that simple. Each point in space that has coordinates, and those coordinates are given because you know where the location is, you're standing on it. Right? If you don't know where you are, look at the ceiling, there's a grid. It will tell you where you are in respect to the corner, which we defined 0, 0 on day 1. So you look at the location, you pick up value for x and value for y for the location from the point, and you plug those x's and y's in those functions f and g, and you compute the vector. Now, what are you doing for that vector? Well, what is it? Is it magnetic field, electric field, gravitational field? Is it drifting currents? Is it, you know, whatever it is? So that's that. And now we're going to have some interesting fields to consider. These fields are, you know, they pop up here and there. We have the most famous are obviously rotational field, radiant field, but you can see other fields as well. So let's take a look at these ones that they give us in the textbook so we can draw the pictures and understand what they are. So here's the first one. It says 0, comma x. You see this one has 0 always for the first. So this field is not moving in the next direction at all. Right? It only has a y component to it. So now, if you want to graph this thing, on the xy plane, you will say, okay, pick 0, 0. If you pick 0, 0, well, your vector is 0, 0. It's a 0 vector, so there's nothing there. So yields vector 0, 0. Pick, let's say, 1, 0. Well, if you pick 1, 0, then your x is 1, so you have 0, 1. Oh, okay. Well, right here at 1, I need to go 1 unit up. If you pick 2, 0, you end up with 0, 2. So if you start at 2, it's 2 units up. If you pick 3, 0, your x is 3. Your coordinate is always 0 on the first one. You plug in 3 for x, you get 0, 3. At the location 3, 0, vector is 3 units tall. If you pick 4, 0, you will get 0, 4, because your x value is 4, and that gets plugged in for the x value, and your first value is always 0, because your vector field says that the first value is always 0. So now when you have that at 4, you have a vector that is 4 units tall. Now, no matter where you are on these vertical lines, the vector field will produce all of these vectors again the same. So the first one is this, and then 3 units, and then 4 units, and so on. But they also go from the other side.
So on the other side of the y-axis, if you same magnitude, just facing the opposite direction then?
Yes. So if you look at this, you can see some kind of motion, right? Now if you pick negative values, let's say negative 1, 0, then your vector is 0, negative 1, and that's this. So now along this line, we have a whole bunch of these small vectors like this. Then there will be these ones, and then these ones.
Why do you always put 1 unit in between?
I can start them anywhere. There is another one starting here and another one starting here. They're everywhere.
Okay.
Infinite, yes. They're starting at every point of a space. I just want to have some kind. The shortest answer is OCD.
Okay.
That's the shortest answer. A quality that not many people share. Or are we? Do you see this is shear? Shear. This is non-claimed homework, so no one cares. Look, this, right? Where one side of the object goes one way and the other side of the object goes the other way. So you get this effect. Right? That's what it is. Should have done on this, because it's already eaten, chewed up. Now I ruined that. But that has no names. It doesn't matter anyway. So there we go. So that's the shear field. Nice. How about vector field given by 1 minus y squared, comma 0. What happened?
I accidentally got enrolled with ruled paper instead of colored paper, and it's just not.
It's equally bad.
What?
The proper math notebooks are the same amount of money in the store, yet you're not buying it.
I have that paper from
I noticed. So now, if we pick 0, 0, So point 0, 0. What's happening with the vector at 0, 0? Well, 0, 0 is here. And we see that the vector is 1, 0. I'm going to use 4 units for number 1. On both y and x-axis. So now we have this vector here. Now let's pick a different value. Let's pick 1, 0. If you pick 1, 0 and you plug the values in, what do you get?
You don't get anything. 0, 0.
Isn't that first vector supposed to be?
Oh, wait. 1 minus 3.
Wait, hold on. Yeah. This is, I have the vector backwards over here, guys. No coughing. 1, 2, 3, 4. 1, 2, 3, 4. So we need to draw a larger picture because everything is, you'll see why. So this is the actually vector, the first vector we put. There we go. So at 1, 0, there's going to be another vector going this way. Great. All right, so let's get off the, if I go to negative 1, 0, I'll still have vector 1, 0. So it seems that anything that I pick along the x-axis is going to have our vector unit long 1, right? Let's go off the x-axis. So how about we pick 0, 1? If I pick 0, 1, now we have a vector 0, 0. Oh, well, that's just going to give us a point there. How about 0, negative 1? That's 0, 0 again. So that's that. All right, so let's pick 1, 1 then, because we can. If you pick 1, 1, well, it's still vector 0, 0. Still a dot.
Okay.
If you pick negative 1, negative 1, it's still 0, 0.
Yeah, exactly. I was going to say. We should do 0, 2.
So it seems that on these lines here, the value of the vector is 0. We have these vectors pushing inside. That one is 1 unit, that one is 1 unit, right? We have those. So how about we try 0, 1/2? This is where the 1/2 is. So what happens at the 0, 1/2? 0, 1/2 is going to give me a vector that says 1 minus 1/2 squared, comma 0, and that vector is 3/4 0. Oh, 3/4 0. Fine, I can get that. There we go. That's 3/4 0. Which is the reason why I drew a big picture. Okay, how about if we pick 0, negative 1/2? It's going to give you the same vector 3/4 0. So we're going to have at 1/2 this one. How about we pick 1/4 as a value? Right, location 1, 4, 0. So that's location on the y-axis. So what kind of vector do we get? We get 1 minus 1/4 squared. That's 1/16. So it's 15/16. Comma 0. The last coordinate for every vector must be 0 because it is, right, given in a vector field that it's 0. So now what I have here is 15/16. That's almost 1. So this number is going to go all the way there and stop. The one on the bottom is going to do the symmetric thing. All right, how about 3/4? If I pick 3/4 0, well, that's going to be 1 minus 9/16. And 9/16 is 7/16, right? 0. If I have 7/16, 0, that's here. Not quite. 7/16 is by 1/16 less than. Yeah.
You're thinking like the quarter comma 0, right? But your function has no x.
What do you mean?
Well, the quarter, like the fxy, you have no x inside of it. So that quarter is 0. Yeah, quarter. Yeah, you're putting the coordinates backwards. When you pick a quarter comma 0, it should be a 0 comma quarter. Because you have your y is within that 3, 1, 0. That's
Those two that you put on top.
the ones you put right underneath the graph.
3, 4.
Oh, yeah. I'm supposed to be at 0. Yeah. 0, 1. Yes. Thank you. Yes, it was supposed to be. Yes. Yeah. All right, good. What is this? It's a flow in a tube. Very good. Now, this is a two-dimensional tube, so it could be the surface of the river. You're always going to have a higher flow in the middle where there's resistance than at the edge, right? Something, well, a 3D tubing, you can, I mean, we are going to upgrade this to 3D, obviously, but, you can think of the blood clots and, water going through the hose or whatever liquid going through the hose. You're designing a fuel system or something, so the liquid is going to move according to this vector field. Now, that means that every particle of that liquid is going to be described through equations using this type of a vector field. So this shows flow. The fastest flow is in the middle, and then the slowest flow is right against the edges where you're having friction between the liquid and the walls of the thing. Therefore,
So you can't go above 1.
what happened?
You can't go above 1.
It's the diameter of
Well, that was the diameter of the tubing. I can increase the tube by simply going into my equation field over here and say, okay, here, 10.
Wait, how do you know that's all?
Right?
So, like, it doesn't have to be given for you to know that?
Well, it's in the.
whatever
It's given in a problem. You will have a tubing that it's, let's say, 4 inches in diameter. If it's 4 inches in diameter, then this number over here will be 2. Right? 4 inches in diameter, radius is 2, so that number would be 2. Great. So this is flow. The last one, f of xy, is given as negative yx. Try to do this one on your own.
Coming? Oh, yeah.
Don't you want to pick coordinates that will give you a vector all in the same direction?
Hey, just pick random coordinates, see what you get. Yes? It's a tedious process.
Oh wait. It's going to spiral, right? Wait.
Up or down, you know?
Yeah. What else do you want?
What's going on?
I don't like this one.
It's not a spiral. It's like this.
I got it. It makes a certain image that
Circles, right?
We really hate circles.
Here, I'll show you. Like, if you do it like this, and let's say I'm gonna call this 1, and all of them are at 1. It's gonna somewhat end up forming like a funny little shape. Oh, you get a nice good shape going.
Yeah. That's the well. It's a standard. All right. Let's see. Let's see what's happening here. So first, we are going to check 0, 0. Right? We start with the origin. When we plug 0, 0, we get the 0, 0 vector. So that's just the point. There is no. Right? Now, let's test 1, 0. And if you test 1, 0, 0 for y, that's that, and then 1 for x, there we go. So at 1, 0, which is here, we get 0, 1, which is vector going up. Then we try 2, 0. We'll get 0, 2. And that's going to go like that. If you try negative numbers, we are going to get 0, negative 1.
It's a spiral. It's a spiral.
It's not a spiral.
Yeah, it's a
It's
a spiral block. Well, yeah, in the Chinese culture.
0, negative 2. There we go.
they're thinking of a different shape.
So now, we can also pick values on the y-axis to see what's happening there. So we have 0, 1. When you plug in 1, you get negative 1, 0. So 0, 1, negative 1, 0 goes this way. And 0, 2 gets negative 2, 0. There you go. And then also, if we choose the negative number, so 0, negative 1, that will give us 1, 0 on a vector, which goes there. And then 0, negative 2 is going to be 2, 0, which goes here. Now, you can pick points anywhere on the, so not only on axes, right? You can pick any point you want. So you can go and let's say you can pick, let's say 2, 2. If you pick point 2, 2, your vector will be negative 2, 2. So if I pick 2, 2, which is this point here, I have to go negative 2 to the left. So that will be this. This point would go like that. This point would go like this. This point would go like this. Ah, no. So maybe now if I erase these guys, you can see that, do you see that there is a rotation to this? That it's trying to spin this way? What's important is that these particles, it's where the, guys, where you, when you pick a point, wherever you pick a point, you see that 0, 0 didn't go anywhere, right? Now, this one is pushing up, this one is pushing left, this one is pushing down, this one is pushing to the right. But then you see these that are not on axes, they're at the angle, right? The whole thing is trying to spin counterclockwise. This is what it's known as a rotational field. Rotational field. And this is one of the main and most used. I mean, if you look at the tornado from the top, what it does, hurricane, what do? They spin, right? So the particles, that would be something to explain that phenomenon. Yeah. Sure. So this is a rotational field.
You pull the thing. You put it in the little fight. Bowl.
The next type
The bowl. I used to.
of the field
Yeah, I just remember.
would be a radial field. Radial field is, okay, radial, it's like it's radiating out of the source, right, around everywhere. So radial field would look like this. You have the vectors coming out, but then those that are further apart, they're longer.
Can you have it that it's the opposite?
Yes.
Is there a different name for that, or is it
Same, just the formula a little bit different. So for radial vector, we have vector xy divided by the magnitude of r raised to some power, and you can mess with the exponent and see what happens. Radius. So you pick a number, 6.
what's that?
P. Yes. So there will be, yes, exponent. So you can put square, but you can also put 1/2. And you can figure out what happens to those. So now that we understand, hopefully, that you are going to have a vector field, and vector field is just an equation in a vector that contains x's and y's, right, which is f comma g, and then you are going to pick points in space, and then whatever point you pick, those are the x and y that are going into the machine, and then the vector field will give you the vector, and that vector, you draw that vector, and then you draw all of the vectors, and you try to make sense of what the field is doing. So now, and then we've seen the shear field, the rotational, then we've seen the radial field and the flow field. So a lot of different fields out there. So now we take all of this and we push it into the third dimension, but just adding simply one more component to it. So vector fields in 3D. All I need to do is to just write the formula, same text, same everything. So formula for, it's going to be x, y, z. It's going to use, it's a vector of x, y, z, f of x, y, z, comma, g of x, y, z, comma, h of x, y, z. And there you go. So that's our 3D case, so R3. And radial field would be the same formula, except it was going to have a Z as well on the top. You can rotate around one of the axes. You can rotate around whatever axis you can think of, right? To make rotational fields. And obviously the graphics in the book will be much better than what we can do by hand. As you can see, the rotational flow, the 3D flow on in that cylinder. Think of a tube, like a blood vessel, right, like veins, or you can think of a garden hose. Whatever it is, you see that the liquid in the center has these very long arrows that's moving the fastest in the center, and close to the edges, the arrows are slower because the liquid is rubbing off of the walls, and the walls and the friction are slowing the liquid down in that area. Observe that the function that used to only be for our two-dimensional motion was just 1 minus y squared. Now you have it's still a downward opening parabola, and we can model that way. Then you can take a look at the other two vector fields, and you see that all the way to the right you have the radial vector field, because the center of it serves as a source, and everything else is going away. What's a good example? A sun, right? Sun is a good example, because it radiates radially around, right, in all directions, the radiation, right? So that's one of the examples. And then we have the gradient and the potential function. Do you see that the vector that you are getting, the vector field, is a collection of functions? You've seen this before, right? So if you have a function, you take partial derivative, what do you to get the gradient? Gradient is also vector of functions in terms of x, y, z. So since gradient is vector of functions, and vector field is a vector of functions, then yeah, we have a function that we call potential function, and when you take the partial derivatives, you take the gradient of that function, you get a vector field. So most of the time we are interested in figuring out the function that generates vector fields, and that's what 14.3 will be devoted to. We are going to learn the method if the field is conservative, and you will see all of those things when we get there. We will devise a method which will give us the opportunity to find the function which generates fields. So you can measure the field by, let's say, if it's a tornado, you throw in a whole bunch of probes inside, and then you get the velocities and you get the positions and all of these kind of things, right, as the wind is.
Or if you want to increase the power of your toilet.
Okay, Rob is thinking on increasing the power of the flush in the toilet, which is also a rotational vector field. Maybe we should get you on that. That's a good project for the next on the next semester.
You say you have someone in your house you want your toilet to be more powerful because of them.
So now we've seen that let's go with a 2D. So we have the xy is going to be f of xy and g of xy. And we also have the notion that del of some function, I don't know what. Well, we use, I don't want to use f because the f is already used up there. Well, I'll use the phi.
What is that now?
Just for you, Liz. So this is going to be phi x, which is actually notation that we are going to see in 14.3, and the phi y. And these are, as you can see, partial derivatives. These are partial derivatives. So I'll just say these are same. In terms of the right-hand side is a vector of two functions. So that function is either given to you or you found it, but they are the same. So there is a connection, right? And this function phi is going to be called potential function. Potential function. So now we're going to say, and here is the official definition. Let phi be differentiable on region in R2 or R3. The vector field F equals del phi is a gradient field. And the function phi is a potential function of f. There we go. So, say temperature function is given by T of xy is equal to 36 minus x squared minus y squared. So this is the temperature distribution. You know that the objects are not heating uniformly, right? If you apply heat to one corner, it will take time for that heat to propagate through the object and make the other side, other corner, more hotter. So now, what am I going to do? Well, I can create the field, right, which would be given as the gradient of the temperature function. And that's simply going to be partial derivative in respect to x, that's negative 2x, and partial derivative in respect to y, which is 2y. So that's that. And we have the field. And that's it. I hope you're not disappointed. We are going to do much more with this in 14.3. Before we get to 14.3, we have to spend an eternity in 14.2. So let's hit the break. When we come back, 14.2, line integrals.